At first glance, the length of a freight train can feel almost excessive. Endless lines of wagons stretching across the landscape, sometimes taking minutes to fully pass a single point. It raises a simple question. Why are freight trains so long? Why not operate shorter trains and more frequently, like trucks on highways? After all, longer trains seem harder to control, more complex to manage, and potentially riskier to operate. And yet, across the world, freight trains continue to grow in length, carrying more cargo over greater distances, with fewer locomotives. This is not sluchinist. It is the result of careful engineering decisions, economic optimization, and deep understanding of how rail systems behave under load. Because in railway logistics, length is not just a characteristic, it is a strategy. To understand why freight trains are so long, we need to look beyond what we see and explore the systems that make it possible. First of all, if you enjoy clear and realistic engineering explanations, leave a like, subscribe to Rail Tech World, turn on notifications, and share your ideas in the comments. Your support helps us continue exploring the hidden systems behind the modern infrastructure that underpin one of the main and safest modes of transportation today. The rail transport. Economy of scale. The primary reason freight trains are so long is efficiency. Moving cargo by rail is significantly more efficient than by road, but that efficiency increases even more with scale. A single locomotive can pull dozens or even hundreds of wagons. This means more cargo can be transported, using less energy per ton, fewer crews, and lower operational cost. Instead of running multiple short trains, railways combine cargo into longer formations, maximizing the output of each journey. This concept is known as economy of scale, and it is one of the most powerful drivers behind long freight trains. Energy efficiency. Rail transport is already one of the most energy-efficient modes of transportation, thanks to low rolling resistance between steel wheels and rails. But long trains push this efficiency even further because aerodynamic resistance is shared across the entire train. The leading locomotives face the highest air resistance, while the wagons behind benefit from reduced drag. This means that adding more wagons does not increase energy consumption proportionally, allowing more cargo to be moved, with relatively small increases in power. Infrastructure limitations. Train length is not unlimited. It is constrained by infrastructure. Passing loops, sidings, station platforms, and signaling systems all impose practical limits on how long a train can be. If a train is too long to fit within these sections, it can block intersections, delay other traffic, and disrupt the entire network. This is why railway systems are carefully designed to accommodate specific maximum train lengths, balancing efficiency with operational flexibility. Distributed power. One of the key technologies that allows trains to become longer is distributed power. Instead of placing all locomotives at the front, additional locomotives are placed throughout the train, in the middle, or at the rear. These locomotives are remotely controlled, operating in synchronization with the lead unit. This reduces stress on couplers, improves traction distribution, and allows much longer trains to operate safely. Without distributed power, the forces inside a long train would become difficult to manage. In-train forces. Inside a long freight train, forces are constantly changing when accelerating. The front of the train begins to move first, pulling the wagons behind. This creates tension forces along the couplers. During braking, the opposite happens. Rear wagons continue moving forward, compressing the train. These compression forces can become extremely large, especially in very long trains. If not properly controlled, they can lead to derailments or mechanical failures. This is why engineers carefully manage how force is applied across the entire length of the train. Braking complexity. Braking a long train is significantly more complex than braking a short one. The braking signal must travel through the entire train. Using the air brake system, this creates a delay, where wagons at the rear respond slightly later. In long trains, this delay becomes more pronounced, which can create uneven braking forces. To manage this, engineers use advanced braking strategies, including distributed power and electronically controlled braking systems, ensuring smoother deceleration across the entire train. Track and terrain factors. Geography also plays a major role. In flat regions, longer trains are easier to operate because forces remain more stable. But in mountainous terrain, things become more complex. Steep gradients increase stress on locomotives, curves introduce lateral forces, and braking becomes more demanding. This is why maximum train length often varies, depending on the route. Operational flexibility. While long trains are efficient, they are not always the best solution. Shorter trains offer greater flexibility. They can move more frequently, adapt more easily to scheduling changes, and reduce delays in congested networks. Railway operators must constantly balance efficiency, capacity, and flexibility, choosing the optimal train length for each situation. Modern monitoring systems. Today's freight trains are supported by advanced monitoring systems. Sensors track wagon behavior, coupler forces, brake performance, and wheel conditions. In real time, this data allows operators to detect problems early and adjust operations accordingly, especially in long trains, where small issues can quickly escalate. Extreme length trains. In some parts of the world, freight trains reach extreme lengths, stretching for several kilometers. These trains are typically used in specialized operations, such as mining transport, where large volumes of material must be moved efficiently. Operating such trains requires advanced control systems, careful planning, and highly coordinated operations, but the efficiency gains can be enormous. Why not infinite length? If longer trains are more efficient, why not make them even longer? The answer lies in diminishing returns beyond a certain point. The benefits begin to decrease while complexity increases. Infrastructure constraints, operational delays, and mechanical limitations all impose practical limits. This is why train length is optimized, not maximized indefinitely. At first glance, freight trains may seem unnecessarily long, but in reality, their length is the result of careful engineering and economic strategy, balancing efficiency, control, and infrastructure limitations to move as much cargo as possible with minimal energy and cost, because in railway systems, length is not just size, it is performance, it is efficiency, and it is one of the key factors that makes rail transport so powerful.